So let us give the proof of the isomorphism extension theorem today. So first we'll write the theorem. Let E be an algebraic extension of F and sigma from F to F prime be an isomorphism. Then sigma can be extended to another isomorphism from E to a subfield of F prime closure such that tau of A is equal to sigma of A for all A in F. So this is the theorem what we stated in an earlier session. So we are going to prove this theorem. The proof of this theorem has got several parts. So what I'm going to do on the right hand side is to outline how we are going to prove this theorem. Then we'll prove each step one by one and come to the conclusion. So we'll start with the zones lemma. Zones lemma. Zones lemma states that if S is a poset and every chain in S has an upper bound, then S has at least one maximal element. The reason why we are going to use this zones lemma in this situation is that we are not sure whether E is a finite extension of F or not. If it's a finite extension of F, we don't need this lemma. So algebraic extension does not imply that it is finite, but finite extensions implies is algebraic. So the way we are going to prove this result is that create a poset using field extensions and isomorphism to a subfield of F prime closure. So the elements of this poset would be an ordered pair with the first element as the extension field and the second element as the isomorphism. We'll create it here. So I'm going to just write the outline first, then we'll take one by one and explain it. Second step is show that every chain has an upper bound in S. And the third step is every chain in S has an upper bound. Okay. Third step is apply zones lemma to establish a maximal element. And our claim is this maximal, the extension field in the maximal element, or the extension field in the maximum element is the whole of E, and the isomorphism in the maximal element is the extension of sigma that we are looking for. That is the claim. So we have a maximal element, and we'll say if the field extension in the maximal element has got two parts. One is the field extension and the second element is the isomorphism. So the field extension in the maximal element, if it is not the whole of E, then show that there exists another element greater than the maximal element. And that concludes the proof. If it shows that you are going to find another element that is greater than, when you say greater than, that is, I'm referring to the relation in the poset. If it's greater than the maximal element, that's a contradiction, and that says that the maximal element is the one which you are looking for this extension of sigma. So we are actually, what we are going to do is we are going to go from sigma, from F to F to sigma, tau from E to a subfield of F prime. So actually what we are going to do is we need to go from, this is our F, E, F prime closure, and this is our F prime. And we already have a sigma here. The idea is start creating extensions of F and sigma like this. Okay, then go all the way up. We are not sure how many times we have to go because we are not sure about the dimension of E over F. But anytime we go like this, we are going to find that there is an upper bound for this kind of chain. Then use the Sohn's lemma. Then we get the maximal element. Then show that the maximal element is the one which you are looking for. That's the idea. So let us create the poset first. So how do you create a poset? The poset should have a field and an isomorphism. So define S is equal to ordered pair. The first element is a field, second element is an isomorphism, and this field should be between F and E. All these are extensions of F. either f or extensions of f. And lambda is an isomorphism from L to a subfield of f prime closure such that lambda of A is equal to sigma of A for all A in F. There are elements here. This is not an empty set. First element is f of f comma sigma belongs to S because f obeys this rule, sigma obeys this rule also. So this belongs to S implies S is not empty. And there are several of them because we already showed that if you take an element outside F and inside E, we can form a simple extension and form an isomorphism to a subfield of f prime closure that can be an extension of sigma. So this set is totally a non-empty set. But this is just a set. We need to create the poset, meaning we need to define a relation. So define the relation in S as follows. If you want to define a relation, you need to take two elements. So let's take L1 comma lambda 1, L2 comma lambda 2 belongs to S. Then the relation is like this. Then L1 comma lambda 1 is less than or equal to L2 comma lambda 2 if L1 is a subfield of L2 and L2 lambda 2 of A is equal to lambda 1 of A for all A in L1. Meaning F, this is my L1 and this is my L2. So this L1 has to be a subfield of L2 and there is a lambda 1 going from here, there is a lambda 2 going from here. So if you take f prime, then this is lambda 1 of L1 and this is lambda 2 of L2. So if you take any element from here and mapping to here, this is actually lambda 1 of that element, then that element is mapped to the same element by lambda 2 also. That's what this is. Meaning lambda 2 lambda 2 leaves L1 fixed. So this is definitely, so S is clearly a poset. We have objects and the relations. So the first part is done. The second part is every chain has an upper bound. By the way, I want to point out a couple of things before we create the chain here. The thing is, let us take an example. This is E and instead of F, we'll say it's Q. And one of the extension of Q is Q root 2. Another one extension is Q root 3. This is probably like this, and this is probably like this. Okay? And you can find another extension of Q root 2, for example, Q of root 2 comma root 3. That is an extension of Q root 2. Here we can take another extension like Q of root 3 comma root 7. So what I'm saying is, in this poset there are elements that are not comparable, like Q of root 2 and Q of root 3 cannot be comparable, meaning there is no relation between these two. This is not a subset of this, and this is not a subset of this. But if you take Q comma Q of root 2 comma Q of root 2 comma root 3, in this sequence of field extensions, everything is comparable. This is a subset of this, so this is a subfield of this, this is a subfield of this, and this is a subfield of this. If you take any of those. So we are going to create a chain. Chain means not like this. This is not a chain, but this is a chain. So we are going to take a chain, like let T is equal to hi lambda I for hi comma lambda I belongs to S for I in some index set be a chain. This is actually a subset of this, but the additional property of T is, if you take any two elements from T, there is a relation between those two. It's either H1, Hi is less than Hj, or Hj is less than Hy. Here it is not like that. Here you can find elements that are not comparable. So that is a chain. We need to find out this chain. This is an arbitrary chain, any chain in S. So we need to find out if there is an element that can be an upper bound of T. So we are going to construct an element of S that could be an upper bound of this. So the way we are going to construct the element from S is, we need two parts. One is the extension and another one is an isomorphism. So let HB is equal to union of I in I, Hi. All the elements of union of all the extensions from T. This is definitely a subfield of E, because each of Hi's are subfields of E. And so we need one more component. The first component is the field, second component is isomorphism. So let's define lambda from H2, because it has to come from L. So this has to come from H. S2, a subfield of F prime closure defined by lambda of an element from an element from H is equal to lambda I of A, where A belongs to Hi. Because if A is in H, that means that A is in one of these Hi's. Actually, not probably in one of these Hi's, probably in multiples of Hi's. For example, if you take f h1 or let's say hi. This is hi plus 1. This is hi plus 2. If there is an element here, that element is also in here and also in here, in all the extensions of hi. So we need to prove that this is a valid definition, because if it is in multiple hi's, this has to coincide. Like this has to be the same element here. Otherwise it is not a valid map. To show that this is a valid map, let A belongs to hi comma hj. That implies hi is less than or equal to hj, or hj is less than or equal to hi. Because hi and hj are coming from the chain. So they are comparable. There is a relation between those two elements. So that implies lambda A is equal to lambda. So this actually implies lambda j of A is equal to lambda I of A, or lambda I of A is equal to lambda j of A. Why? Because of the definition of the poset, the relation of the poset, and that implies lambda I of A is equal to lambda j of A, and that is equal to lambda A. So it's well defined. Now it is just a map. Okay, we need to still show that this is an isomorphism. Otherwise, h comma lambda cannot belong to S. This is an isomorphism. A lambda from L to subfield of is an isomorphism. You can still write it here. Lambda is an isomorphism. So our next step is to show that lambda is an isomorphism. So how do you show a map is an isomorphism? First we show that it's a field homomorphism. Then we need to show it is a 1-1. So to show that it's a field homomorphism, take two elements. So let A comma B belongs to H, and that implies A belongs to Hi and B belongs to Hj, and that implies A comma B belongs to either Hi or Hj. So that means lambda of A plus B is equal to lambda I of A plus lambda I of B, or lambda j of A plus lambda j of B, because lambda i's and lambda j's are isomorphisms. And that implies lambda of A plus B is equal to lambda of A plus lambda of B. Similarly, lambda of AB is equal to lambda of A times lambda of B. So lambda is a field homomorphism. Now we need to show that it is 1-1. How do you show it's 1-1? Let's take the kernel of lambda is equal to A belongs to H such that lambda A is equal to 0. and that is equal to A belongs to H such that lambda I of A is equal to 0 for some I in I. And that is equal to, because lambda I is an isomorphism, this is the kernel of lambda I, and that is equal to 0. That implies lambda is 1, 1. And because we are defining lambda to a subfield of F closure prime, we don't need to show that is a onto function. So that implies lambda is a isomorphism from H to a subfield of F prime closure. So that means H lambda belongs to S. That's all we showed so far. Now we need to show that H lambda is upper bound. That is very easy, because since Hi is a subfield of H for all I, and lambda of A is equal to lambda I of A for some I in I, definitely clearly Hi comma lambda I is less than or equal to H comma lambda, and that implies H comma lambda is an upper bound of T, and T is an arbitrary chain in S. That means every chain in S has an upper bound. So what we have showed so far is this is our F, and this is our E, and this is our F closure, F prime closure, and this is our F. And we have a sigma here. And what we did is we took a chain from S, and those are, see, one of the member is F lambda. So another member is L1. H1 lambda 1. This is our H1, and lambda 1 goes from here. Lambda 1 goes from here to here. Lambda 1. And this is actually our, this set is going to be lambda 1 of H1. And we took another extension of H1 like H2. This is H2 of lambda 2. This is H2. Actually, this is H1 and this is H2. So these are objects from S. So lambda 2 goes from here to another extension of this. So this is H2, and we had a map from here to here, that is lambda 2. So these are all chains. So we went like this, and it goes on, and we saw that there is an upper bound for this kind of sequence, and probably it may not even reach here. Assume that we are not reaching here, we are reaching very close to this, it hasn't reached yet the E. So we are going to use the zones lemma because this has got an upper bound. So there is a maximal element exists. So this is not a single chain. There are multiple chains. Probably there is another extension of f, let's say h prime 1 of lambda prime 1, or h prime not, h prime is an extension of f that does not contain this h1 prime and h1 are not comparable. It's a totally different chain. This is q of root 2, this is q of root 3, something like that. So this is going to be like this. And here also, this also has another extension, that is h prime 2, then h prime 3, dash dash, it goes there. That also has an upper bound. So for all these upper bounds, there is a maximal element here by zones lemma, and that is what we are going to take. So it is not a single chain. There are several chains in these extensions, in this poset. If you take any chain, there are multiple chains. If you take any chains, every chain has an upper bound, so there is a maximal element. Okay? So when you are going to apply the zones lemma, so let's say let K tau be a maximal element in S. That is, I'm not going to write the other part of the isomorphism. This is our E, this is our F, and K is very close to E. This is our K. Okay, if K is equal to E, we are done. So if K is equal to E, the theorem is proved. There is nothing else to prove. So K is our K is equal to E, and tau is the desired extension of sigma that goes from E to a subfield of F. So let us assume that they are not equal. So assume K is different from E, but K is always a subset of E, subfield of E. That implies there exists an alpha belongs to E minus K. That is somewhere here. And that implies alpha is algebraic over K. Why? Because E is an algebraic extension, so any element from E is an algebraic over F, so it is also algebraic over K. And that implies there exists a polynomial P of x, and that is the irreducible polynomial of alpha over F, and let it be equal to a0 plus a1x1 a1x plus dash dash an x to the power of n be the irreducible. Okay, this is an irreducible polynomial. There is an irreducible polynomial such that P of alpha is equal to 0. So this is our alpha, and there is a irreducible polynomial over S where ai belongs to k. Sorry, a belongs to k, yes. Now we create another polynomial in a subfield of f closure, f prime closure. I'm going to write it to the left side. The isomorphisms are going from here to here. So what we do here is let k prime is equal to tau of k. So this k is actually mapped to a tau prime, another subfield of f closure, f prime closure. That is, we'll say that it is a k prime is equal to tau of k. Okay. Now, so this actually belongs to, we can say p of x actually belongs to k of x. So let us create another polynomial. Let q of x equal to tau of p of x, and that is equal to tau of a0 plus tau of a1x plus dash dash tau of an x to the power of n. See, these are elements from x, k. A's are from k. So tau of ai's are from k prime. So for ai's belongs to k prime of k prime, and that implies q of x belongs to k prime of x. This q of x is irreducible. Why? Because we got q of x from an isomorphism of an irreducible polynomial. If this is not irreducible, q of x can be factorized, and so if you take the inverse of the tau, we'll find that p of x is reducible, which is not right because p of x is an irreducible polynomial over k of x. So q of x is irreducible, and that implies there exists an alpha prime in f prime closure that is a 0 of q of x in k prime of x. So that means there is a, for each alpha in E minus k, there is a alpha prime here. Okay, and the beauty of this one is degree of alpha over k is equal to degree of alpha prime over k prime, and that is equal to n. And it's because this is the irreducible polynomial. So now what we do is define an isomorphism. Define an isomorphism. Actually, I'm going to define a map. I'm going to give you an exercise to prove that it's an isomorphism. We have done it earlier, so I'm not going to do that proof again here. Isomorphism from the simple extension of alpha to the simple extension of alpha prime. See, this is outside of k, so we can still consider this as an extension. This is actually k of alpha, and this will be k prime of alpha prime. by simple extension. Let's take toe bar. By toe bar of what is an element here? It will be a polynomial in alpha whose degree is less than n. So that is 0 plus c1 alpha plus dash dash cn minus 1 alpha to the power of n minus 1. That is a general element in here, equal to all these C0s are from K, or CIs are from K. Okay? So, how do you define the map? It's actually toe of C0 plus toe of C1 alpha prime plus dash dash toe of Cn minus 1 alpha prime n minus 1. Each of these toe of Ci's, each of toe of Ci's are from K prime. So definitely this is an element in here. So then toe bar is an isomorphism. So that means, that implies K of toe is less than K alpha of toe bar. Okay, I'm going to gain one more step. I want to write it here. And isomorphism, and therefore that implies K of alpha comma toe bar belongs to S. And K of alpha or K comma toe is less than or equal to K alpha comma toe bar. And that contradicts. So that means K comma is not maximal. It's a contradiction. And why we got this contradiction? Because we assume that K is not equal to E. If K is equal to E, we are done. If K is not equal to E, then we are arriving at a contradiction saying that it's not maximal. And that concludes the